Hi, I'd like to take a minute to talk about what I like to refer to as Looney Tunes physics. When we get to the quantum world, we can't always use analogies to the classical world to explain what's going on. But for some physical phenomenon, it ties into things that you've seen illustrated sometimes in cartoons. So if you were to take electrons, and you were to try to contain electrons through little tiny walls, there is a probability that that electron would escape, or some fraction of the number of electrons confined in similar cages would be able to escape through that barrier if it's not infinitely high. Now, if you were to also have, say, a free electron that were traveling, but then it changed in its total potential energy relative to the Hi, I'd like to talk about a physical phenomenon that sounds a lot like an episode of a classical cartoon show. Now, whenever we get to the quantum world, things get really weird. Wave functions can extend into space where these waves normally wouldn't occupy, and what that means is we can observe interactions happening in areas where classically they wouldn't be allowed. Well, if we happen to have a very, very narrow barrier, that wave function can extend through the barrier, and there is a likelihood that an object would be able to, say, tunnel through a barrier. Similarly, if an object had a kinetic energy, if the potential energy changed, then there's the possibility that object could reflect. So an example of the reflection problem is, imagine you're watching a cartoon set in the American Southwest and a very clever canine character decides to try to throw a brick off a cliff. There would be a probability of that brick, if it were a quantum object, bouncing back and hitting him in the face, which from the cartoons, of course, is going to happen. Now, if that scares the very fast-running, flightless bird that such a canine might be pursuing, it might take off and run towards a cliff. And then, of course, if it looks like a hole, the fast-running bird makes it through, and then the clever canine will end up plastered on the side. In the quantum world, both of those ideas can happen. And for the case of tunneling, the number of electrons that would be able to tunnel through a barrier can be calculated, at least as a fraction, where the tunneling fraction is equal to Euler's number to a factor of -2 times a tunneling coefficient c times the thickness of our barrier L. So say we have a barrier of a thickness of 1.1 nanometers, and our electron has a kinetic energy of 40 electron volts in a region where there is 0 potential energy. And it encounters a barrier with a potential energy of 60 electron volts. Well, we would calculate our coefficient C by taking the square root of 2 times the mass of our electron times the difference between the potential energy and the kinetic energy of our electron, and then we would divide that square root by h bar, Planck's constant divided by 2 pi. So our coefficient for this particular electron encountering this obstruction would be 2 times 9.11 times 10 to the negative 31 kilograms. 60 minus 40 gives me 20 eV. I'll need to convert it into joules, so I'll multiply by 1.6 times 10 to the minus 19 joules per electron volt. I'll take the square root, divide by h bar, Planck's constant over 2 pi, 1.054 times 10 to the negative 34 joule seconds, and I end up with a coefficient that's equal to 2.29 times 10 to the 10 inverse meters. So if my barrier is 1.1 nanometer, I multiply this by 1.1 times 10 to the negative 9, and then multiply it by 2, and I get a factor of 50.4. Now if I take e to the negative 50.4, I get a pretty small number. 1.36 times 10 to the negative 22. So if you were to send a mole of those electrons at that barrier, about 60 will make it through, which isn't a lot at all. But the thinner we make that barrier, the higher the likelihood it is that tunneling's going to occur. So if I were to instead shrink that barrier to the approximate radius of a hydrogen atom, 0.053 nanometers, then my tunneling coefficients become 2.43 when I multiply everything together. And e to the negative 2.43 gives me 8.84%. So the thinner the barrier, the higher the fraction is of the number of electrons that would end up making it through. And there are some devices that rely on quantum tunneling as a way of establishing a current through an otherwise unallowed region. So to just wrap up with the cartoon, so if our clever canine were to decide to pole vault, well, classically, if he were up here, he'd get over, but quantumly, of course he could bounce off the cliff even though he's cleared it because of that reflection effect I talked about before. Quantum's kind of weird. Thanks for watching.